Now, from continuation of the previous lecture, we are trying to derive in the packed bit. So here the topic is same, that is the continuation part of the previous lecture, packed bit reactor design, external resistance mass transfer. Now, for this reason, we consider a reaction that A plus B gives you C plus D, and here the fluid is flowing in this side, and the products come from this side, and the packed bit is with the multiple catalyst particles. And in that case, we consider the segmental height and do the mole balance equations. And from these mole balance equations, this is the mole balance equation what we get in the previous class, that is minus 1 by AC dFZ by dZ plus RA double prime into AC equals to 0. And we try to develop the concentration profile. To develop the concentration profile, we convert the APZ and RAZ to the concentration, and if you and we substitute that concentration term in that mole balance equation, we in the last class we develop the concentration profile. So in the last class, what we get, this is your concentration profile. We try to develop. This is your concentration profile. So Ca minus by Ca naught equals to exponential AC into AC divided by U into Z. Now here, this comes by integrating this equation. Now here you can see that that concentration profile is a function of Kc, AC, U and Z. So Z is actually in terms of, you can say, the length of the packet reactor, and AC is the external surface particle per unit volume of the reactor. AC is mass transfer coefficient. U is superficial velocity, and Ca naught is initial concentration, and Ca is concentration at any. Now, up to this, what we learned, that is, as the reactant passes from length 0 to 1, the concentration of A is getting decreased as the A is getting consumed, and it's converted to the product C and D. So gradually the concentration is gradually decreased towards the length. Now come to the next part, that is, after finding out the concentration profile, our aim to determine the length of the reactor to achieve a certain conversion, or vice versa. If the length is given at that certain length, what will be your conversion can be achieved? Or if the conversion is given, what can be your packed bit length, and what is the maximum weight you can consider inside your packed bit reactor. So in that case, we know what is conversion. Conversion is X. X is nothing but 1 minus Ca by Ca naught. 1 minus Ca by Ca naught. So how much reactant A is converted to its product. So that is conversion. We all know these things. So what is Ca by Ca naught? Ca by Ca naught equals to 1 minus X. So substitute here. If you substitute that Ca by Ca naught here, we can get the equation in terms of conversion. So the equation we can get in terms of conversion here. So that is actually ln of 1 minus x equals to minus kc ac u by z. And if you remove the negative sign, so the equations comes, that is ln of 1 by 1 minus x equals to um, KCAC by Z. So in that, here you can see here that conversion is gradually increasing as the length is goes from 0 to 1. The conversion is gradually increased. Now at Z equals to L, so at Z equals to L, we can say x equals to xl. If z equals to sorry, here one mistake is claims here, so just ignore this and what I'm telling, just listen. So when z equals to l, x equals to xl. So if you put this equation here, so the equation will comes again, ln of 1 by 1 minus x, 1 minus xl equals to kc ac u, u into L. So Kc Ac u into L, ln of 1 by 1 minus xl. So this equation actually just substitute x in terms of xl and z in terms of L. So from this equation you can get that L equals to u into Kc Ac ln of 1 by 1 minus xl. So this is one equations. So you can see that at whatever the, suppose your conversion is 70%, 70% conversion you can achieve. 70% conversion you can achieve. So for this 70% conversion, if the other parameter is known to you, you can be able to find out the length of the reactor. So AC is actually what? So AC is external surface area of the catalyst per unit volume of the reactor. So that can be easily find out by characterization of the catalyst. From BET surface area, you can be able to find out the external surface area of the catalyst. U is nothing but the superficial velocity. So from the fluid flow rate, we can be easily find out the U, and Kc is the mass transfer force coefficient. So that is quite required the correlation. So I will come later for the about this correlation. So that is need to determine, that Kc is need to determine. So if all the parameters is known, so we can be easily determine the length of the backbed. So from this equation, same way, if it is a inversion is happens, so if the length is known, how much conversion can be achieved? So if you reverse this equation, you will get this uh, equation in terms of length to find out the conversion. So from this equation, we can see that conversion is a function of Kc, Ac, U, and L. So as I told you that L, U, and Ac can be known to us. But what about this Kc? So to find out the Kc, we need a correlation. Kc is actually, what is Kc? Kc is mass transfer coefficient. So Kc is mass transfer coefficient. So to find out the mass transfer coefficient, we need correlation. This is called as a Thomas-Kramer correlation. So Thomas-Kramer correlation is mostly applicable to find out the mass transfer coefficient for packed bed and fluidized bed. Now, previously, we have learned about the cross-link correlation. As I told you, up to this, we have learned single particle. When the fluid is going over the single particle, what will be the concentration profile? How the mass transfer coefficient can be determined? The mass transfer coefficient can be determined by using the cross-link correlation. But when you are talking about the backfed reactor, so it is a full of several particles. So in that case, we have to modify this cross-link correlation so that we have to consider the bed velocity, the state factor of the particle, so that we can get the mass transfer coefficient. So here already about the cross-link correlation. The cross-link correlation is actually what? Series number equals to 2 plus 0.6 number to the power half, schemic number to the power 1. So that we come to know. So what, and from there series number is Kc dp dab. Reynolds number is u dp by nu, and schemic number is nu by dab. Nu by dp. So from there you can see all are the intrinsic property of the fluid. dab is the diffusivity of the fluid, nu is the viscosity of the fluid, dp is the particle diameter, and u is the fluid flow, that is you can see the velocity of the fluid. So only all are the intrinsic property except Kc. So if you put that here, so Absolute number is CdP by DAB plus 0.6. Reynolds number is by gamma and limit is gamma by T. So all these things is known to us. So from this, we can be easily able to find out the values of mass transfer coefficient. But same way, actually, we can be able to find the coefficient for the packed reactor, but only few modification has been done. Here we have to consider the bed porosity because the bed is filled with several multiple particles, so there is a porous porosity is a very vital factor in that case, and another one is the step factor of the particle. So the modified equation for the frosting correlation of modified equation is called as a Thomas-Kramer correlation. So here the modified equation is Reynolds number prime equals to 1.0 Reynolds number prime to the power half, Schmidt number to the power one third, where Reynolds number prime is Reynolds number into phi by 1 by phi into 1 by safe factor. So phi is actually here the bed porosity. Phi is here the bed porosity, that is fraction of the void present in the bed. Fraction of the voids present in the bed. So that can be find out from the volume of the particles divided by total volume of the particles divided by the total volume of the bed. That gives you the fraction that is occupied by the catalyst. So 1 minus that fraction occupied by the catalyst gives you the fraction of the that is void fraction of the bed. So this is the phi, and this is the factor of the particle. So because all the particles are considered as a spherical particle, but though in reality all the particles are not in the spherical particle, so in that case you have to consider one a shape factor. And Reynolds number prime equals to Reynolds number divided by 1 by phi into shape factor. So if you substitute this all the things here in that equation, Thomas-Cranmer correlation, so one can get this equation Ac dP by dAV into phi by 1 minus 9 into 1 by shape factor equals to U dP by mu into 1 by 1 phi into shape factor to the power half. So this is nothing but the Reynolds number, this is limit number, and this is the root number modified. Modified root number and modified Reynolds number. And when we can see that all the things are known to us except the Kc values, because all of the intrinsic properties of the fluid are as well as the catalysts. So if we know values, we can be easily able to find out the Kc value. So if we are able to find out the Kc value, if we put the Kc in that equation, so in the equation 12, so N equals to U by Kc Ac into ln of 1 by p minus xl. So I can find out the length of the reactor. So whenever we are trying to find out the length of the packed reactors, sorry, here is one mistake there. So instead of del Kz, if you multiply by L into C, AC is the L into AC, AC is the cross-sectional area of the pack. L into AC cross-sectional area of the packed bed, that gives you the volume of the reactor. So volume of the reactor gives you length of the packed bed into AC. So don't vote for this delta Z. I do the mistake here. So that will be cross-sectional area into length gives you the volume of the reactor. Now, if the bulk density of the catalyst is known to you, that is density is given, bulk density can be find out by the characterization part known to you. So that is kg per meter cube. So you can be easily find out the how much weight is required for the packed weight for achieving this much conversion. So this is all about the packed bed reactor design part. First we are going to try to develop the concentration profile. From this concentration profile, we are trying to convert that equation in terms of conversion and length. And if the certain conversion is known, we can be able to find out the how much length is required to find out this conversion. Again, if the length is known, we can say that how much conversion can be achieved. Now, to find out this length, to actually how much weight is required in the catalyst, we should know the volume of the reactor. To get the volume of the reactor, we should know the length of the reactor. To length, so that is the equation for the length of the reactor. And for this length of the to find out the length of the reactor, we need to find out the mass transfer coefficient. So that mass transfer coefficient can be found out by using the Thomas-Cramer correlation. So thus we conclude today's session. So next class we will try to solve a few numericals based on this theory. Thank you.